This question involves a variable force that needs to be handled using differential equations, but we need to do a little bit of work before we get there. First part of the question is finding an expression for velocity. That'll involve a couple of methods. The force equals mass times acceleration comes into most of these questions, some initial conditions, as well as the partial differential work we did in the previous unit. This question basically connects a mass with a force and acceleration consideration, practical question. It's important to notice this question here talks about friction. Friction's a retarding force, so the best approach mathematically is to make it, just to put negative signs in everywhere, okay? So in all the questions we do, the force will be either, or the net force, the overall force, will either be pushing something faster or slower. If it's faster, then it's positive. If it's slower, then it's negative. We use the F equals ma expression again in this question here. We've got our force and we've got our mass. Acceleration comes out to be this value here, which is the previous values divided by 5. Once we've got this expression for acceleration, it flips over to become a differential style question. We use the relationship that acceleration is the derivative of velocity, with that line there, and we go ahead and then basically try and solve down through these parts here using our partial derivatives. It is important, really important in these questions, that even though it's tempting to try and do something and you're working with that, okay, with a negative 0.04 v minus 1, so that later on when we do some of the work with the integration expression, it's really important to get single v on its own. Okay, so in this case here it's v plus 25 because I pulled a negative factor out the front. But this bracket, having a single term of v, is probably the most important part of all these questions that you can work on. Now, using the expression we got on the previous page, okay, we're going to break it apart into the differentials. And then we're going to integrate both sides. So you'll see the dt and the dv, okay, swap sides, okay. Basically that's achieved by taking the dt, well, I think you can see how you do it, but basically the dv that's up there has this term brought over there, and the dt that's down there swaps over to this side and sits after the 0.04. So we end up with this expression here. And then by integrating both sides, this side with respect to time and this side with respect to v, we get an expression here, noting that we do in fact include an integration constant in there. But what's important, and this comes back to the simplicity of that v plus 25 on the bottom, means that the answer to the right hand side when we integrate is a natural log of v plus 25. If you've got anything in front of the v, okay, a negative value or another numeric value or whatever, it I won't say it destroys the natural log, but the best thing to do is to bring in this case here, if you had a 2v, so if we had the integral of 2v, and that was something like that, so we had 2v plus 25 on the denominator, you'd want to bring the 2 over there, but that would impact on that would become 12.5. But at least then you'd have v plus 12.5, and the 2 out the front would just sit there and wait for the integration to be finished, and your answer down here, you'd have a 2 in there. So that's what you need to do with those ones. But the best thing to do is to bring it over into this line of working here with v already worked out to be just on its own. We raise both sides to an e, that is we raise both sides to the power of e. So on this side here, you add e to the power of everything else, but on the other side the e's and the natural logs cancel. Now, quite a lot of time people forget where a comes from. A does not come from outer space. A is a result of the e to the power of c term. It's written over here. Okay, a is e to the power of c. Because if I was to break this apart again, it could be written as e to the power of this thing plus c. So that would be e to the power of that thing times e to the power of c. Well, e to the power of c is equal to a. So that's where we get that from. Now we use the question's initial values to try and work out what a is. And in this case here, when we start, it had a speed of 14. So we're going to use our velocity expression, v equals, it's the thing that we were working through with the unknown of a and t of 0. What you'll end up getting is that a equals 39, and this allows us to come up with a final expression there of this thing here. I think the book is wrong. The book mentions that that should be, I think, 1/35, but in fact the correct answer is 1/25 or 0.04. So we've got our expression for velocity. So the previous part A of the question was about finding an expression for velocity. Part B relates to finding a distance when the velocity is 0, or that is when, how long does it take, how far does it take for the object to stop. Really has to do it in two parts. First of all, we need an expression for displacement, and we know that displacement is found by integrating the velocity with respect to time. So we take our v term and then we do a fairly routine integration. You'll see that the effect of integrating this thing, well, to achieve this integration, you use this little rule here, which we've done before, and if you need it, I'll give it to you in my formula sheet. But it basically involves taking the power and plonking it underneath, so that if we were to find the derivative of this thing using the chain rule, you'd end up with a 0.004 out front, 0.04 out front, and they'd cancel with those two. So whilst integration is more complex than differentiation, trust your rules, and also remember you can always verify that you've got the right answer by backtracking and finding the derivative of the integral. But in any case, we end up with an expression here that that has, I guess, a series of t terms. I've just cleared that writing out so that we can clear it out. So we've got this expression here, which is for displacement. The purpose of the displacement expression will be to solve it for t. So our aim next is to work out how long this thing takes to finish, and then we're going to work out a displacement. Of course, we've still got a c in there, so we need to solve it for c first. Again, we use initial conditions. Time is 0, displacement is 0. So when you substitute a 0 in for time everywhere, and a displacement for 0 everywhere, a displacement as 0 everywhere, you end up getting this expression for c, and then we plug it back in, and we've got ourselves a pretty good looking displacement expression down the bottom there. The expression for displacement that we found on the previous page involved substituting a t value in. So we need to know how long it takes for this thing to reach a velocity of 0. We use our previous piece of work that involved finding an expression for v, insert 0, and we're going to solve for t. And you end up with a bit of maths down here. You end up solving with 11.18 seconds. Okay, that involves a little bit of manipulation, but ultimately it should be routine enough to find t. It's all written there for you. Once we've got a t value, we then substitute it into our displacement value, our displacement expression. A little bit yucky, but you end up with a 72.1 metre distance travelled, which is the answer to this question. Well done. Go directly to go. Collect $200. Pay taxes. Be good citizens. Good evening.